Dark matter and dark energy. When we look up into the night sky, we see a universe teeming with stars, galaxies, and nebulae, an intricate cosmic dance illuminated by distant lights. But this vibrant view conceals a deeper mystery, one that challenges our fundamental understanding of the cosmos. It is the enigma of dark matter and dark energy, two invisible phenomena that dominate the universe and shape its destiny. In the 1930s, astronomer Fritz Zwicky made an astonishing discovery while studying the Coma Cluster, a vast collection of galaxies. He observed that galaxies within the cluster were moving far too swiftly to be held together by the gravitational pull of visible matter alone. It was as if an unseen mass, far more substantial than all the stars and gas combined, was at work: dark matter. Later, in the 1970s, Vera Rubin examined the rotation curves of spiral galaxies and found something similarly perplexing. The stars at the edges of galaxies, instead of slowing down with distance as expected, maintained rapid orbital speeds, a clear indication that a halo of dark matter surrounded and influenced them. This dark matter, unseen and undetectable by conventional means, reveals its presence through its gravitational effects. So, what is dark matter? It doesn't emit, absorb, or reflect light, making it invisible and enigmatic. Its nature remains one of the greatest mysteries in modern physics. Scientists have proposed various candidates: WIMPs, weakly interacting massive particles, axions, or even primordial black holes. But, despite decades of searching, dark matter continues to elude direct detection, with experiments located deep underground and in space tirelessly hunting for its telltale signs. But the mystery doesn't end with dark matter. In the late 1990s, astronomers studying distant supernovae made a groundbreaking discovery. The universe is not just expanding, but doing so at an accelerating rate. This acceleration implies that some unknown force, dubbed dark energy, opposes the gravitational pull of matter, pushing galaxies apart with increasing speed. Dark energy accounts for about 70% of the universe's total energy content, overshadowing both dark matter and normal baryonic matter, which makes up just a small fraction. It remains an enigma shrouded in mystery. Much like dark matter, its nature challenges our understanding of fundamental physics and cosmology. Several theories attempt to explain dark energy. One notable explanation is the cosmological constant, a term introduced and later retracted by Einstein, re-embraced to describe this mysterious force. Alternatively, some physicists propose that dark energy might be an evolving field known as quintessence, changing in strength over time and influencing cosmic expansion in complex ways. Dark matter and dark energy paint a picture of a universe where most of the constituents remain unseen, detectable only by their indirect influence on cosmic structures and expansion. Galaxies cluster together due to the gravitational embrace of dark matter, forming large-scale scaffolding that shapes the observable universe. Meanwhile, dark energy governs its fate, deciding whether the universe will expand forever, eventually fall into a big freeze, or experience another dramatic fate. To explore these cosmic mysteries, scientists utilize cutting-edge technology, telescopes mapping the skies, sophisticated detectors in hopes of capturing dark matter particles, and large collaborative data collection like the cosmic microwave background radiation and galaxy surveys. These efforts aim to unveil the universe's unseen architecture and unravel the nature of this dark sector governing evolution. The study of dark matter and dark energy not only deepens our understanding of the cosmos, but also invites profound philosophical reflections. It serves as a humbling reminder that what we can see and touch, these stars, planets, and dust, is merely a tiny fraction of the grand cosmic tapestry. It challenges us to delve deeper into the unknown, probing the limits of observation and theory. In our quest to comprehend the universe, dark matter and dark energy stand as reminders of the mysteries yet unsolved, of forces and forms that lie beyond the veil of perception. They propel our scientific inquiry, inspiring creativity and innovation. It's a journey fueled by curiosity, a pursuit to illuminate the darkness and grasp the unseen threads that weave our universe together. Whether through giant telescopes scanning the heavens or detectors sitting quietly in subterranean labs, we continue our search, driven by the hope that one day we might unravel the secrets of the invisible universe that cradles the stars. Emergence of consciousness. Consciousness is undeniably one of the most profound and perplexing mysteries of the universe, sitting at the crossroads of biology, physics, and philosophy. It is the state of being aware of ourselves and our surroundings. Yet how this awareness arises from the workings of the brain remains a puzzle that has fascinated thinkers for centuries. To explore this enigma, we begin with the human brain, a marvel of biological complexity containing approximately 86 billion neurons. These neurons communicate through an intricate network of synaptic connections, creating patterns of activity that underlie thoughts, emotions, and actions. While neuroscience has made remarkable progress in mapping these physical structures and observing brain activity, it struggles to answer why these processes result in subjective experience, the hard problem of consciousness. One intriguing framework attempting to address this is Integrated Information Theory (IIT), which suggests that consciousness arises from the integration of information within a complex system. According to IIT, any sufficiently interconnected and organized system, like the human brain, possesses some level of consciousness. This theory provides a mathematical approach to understanding awareness, suggesting that consciousness is not an all-or-nothing phenomenon, but exists on a spectrum. Another theory delves into the quantum realm, proposing that consciousness may emerge from quantum processes within neurons. The Orchestrated Objective Reduction (ORP) theory, proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff, posits that microtubules, tiny structures within neurons, utilize quantum effects to generate conscious experience. Though controversial, this idea links the mysteries of quantum mechanics with the mysteries of the mind, offering a radical perspective on consciousness. Philosophical perspectives like panpsychism take the question even further, suggesting that consciousness might be a fundamental property of the universe, much like space and time. In this view, all matter, from the smallest particles to the largest celestial bodies, possesses some degree of consciousness. While this idea challenges conventional thinking, it offers a compelling alternative to purely mechanistic explanations. The rapid advancement of artificial intelligence also forces us to reconsider the nature of consciousness. As machines develop increasingly sophisticated cognitive abilities, questions arise about whether they could ever achieve true consciousness, or whether awareness is unique to biological systems with specific neural architectures. Could AI one day possess not just intelligence, but subjective experience? The emergence of consciousness invites fundamental questions. Why do we experience anything at all? Is consciousness an evolutionary adaptation that enhances survival, a byproduct of complex neural networks, or an emergent property of the universe's underlying laws? These questions not only push the boundaries of science, but also challenge our understanding of what it means to be alive and aware. Though we have yet to fully understand consciousness, every discovery brings us closer to unlocking its mysteries. This journey is more than an academic pursuit. It is a quest to understand what makes us human. Consciousness allows us to reflect on the universe, our existence, and the profound beauty of being aware. In seeking its origins, we delve into the essence of who we are, exploring the intersection of mind, matter, and the infinite complexities of the cosmos. time, it's something we all experience, from the rhythmic ticking of a clock to the gradual aging of our bodies. But what is time, really? It's a question that has perplexed philosophers and scientists for centuries. We live in a universe where time marches relentlessly forward, past, present, future. Yet, when we delve into the fundamental laws of physics, time seems to be an equal opportunity player, showing no definitive preference for moving forward or backward. Whether you're looking at Newton's laws of motion or even Einstein's relativity, what happens in reverse is every bit as valid, according to these laws, as what happens when the usual forward sequence unfolds. So, why do we experience time as linear and sequential, with an undeniable arrow moving only forward? One notion is tied to entropy, a concept born from the second law of thermodynamics. Entropy measures the level of disorder within a system, and the law states that in a closed system, entropy can only increase. Imagine a pristine sandcastle dotting a windswept beach. Over time, wind and waves gradually erode its meticulous edges, inevitably increasing the disorder. Ultimately, the grains of sand flow back into the larger chaos of the beach. The passage from order to disorder lends time its relentless directionality, from yesterday to today and onward to tomorrow. Yet mysteries remain. Why did the universe start in such a low entropy, highly ordered state? If time flows from order to disorder, what set the cosmic clock ticking with such an exquisitely structured beginning, as seen just after the Big Bang? Some suggest that the universe is an entropy-generating machine. As it expands, it creates new space, offering more chances for entropy to increase, a cosmological balancing act across an infinite canvas. But physicists like Julian Barbour have proposed a more unsettling idea. What if time, as we perceive it, doesn't exist? Barbour envisions a timeless landscape where what we see as past, present, and future stand together in a frozen tableau. Each moment exists simultaneously, like frames on a film reel. We perceive them in sequence because of our consciousness, tricking us into seeing time as a river in constant flow. In this viewpoint, the arrow of time is a powerful illusion, a trick of perspective woven by our mind. Moreover, the notion of a multiverse complicates things further. What if countless universes exist beyond our own, each with different laws of time and space? In some, the arrow of time might not point forward at all. Perhaps our universe is simply a rare statistical anomaly, a serene bubble of time-oriented order bobbing within a sea of chaos. In search of answers, scientists study the frozen landscapes of theoretical physics, hoping to glimpse behind the curtain. But for now, time remains an unpredictable enigma. Will we one day see the mechanics behind time's arrow, bending it to our will? Might future technology unlock time's mysteries, allowing us to step back along distant ancestors or leap forward into an uncharted future? This tick-tock of curiosity keeps our minds racing, pulling us ever onward. In our daily lives, time is a guide, a backdrop to our memories and dreams. It drives us toward what lies ahead and anchors us to what has been. Whether it's a cosmic arrow or a mental construct, time shapes our existence, urging us to embrace each moment while pondering all of its intrinsic possibilities. Each tick of the clock, every passing season, whispers this existential truth. Time is precious, fleeting, and mysterious. Time, the ever-present heartbeat of the universe, remains an enduring enigma, one that guides, challenges, and captivates our collective imagination. Matter-antimatter asymmetry. Imagine for a moment a universe just after the Big Bang, a seething cauldron of primal energy where matter and its twin antimatter were created in perfect harmony. According to the fundamental laws of physics, every particle of matter, the protons, neutrons, and electrons, has an antimatter counterpart, an antiproton, an antineutron, and a positron. When these two meet, they annihilate each other in a burst of pure energy, a radiant disappearance, leaving nothing but light in their wake. In this symmetrical cosmos, you might expect equal amounts of matter and antimatter to exist, meaning that all matter should have self-destructed almost instantly, leaving a universe filled with energy, light but devoid of form, the matterless cosmos. Instead, something curious happened. For every billion matter-antimatter pairs generated at the dawn of time, one extra particle of matter remained unpaired, unannihilated. This seemingly insignificant imbalance, a tiny tilt on the grand cosmic scale, defined everything. It is why the stars twinkle in the night sky, why galaxies are drawn into intricate swirls, and why life ultimately emerged on Earth to ponder these mysteries. But why? How did this slight excess of matter over antimatter come to be? Exploring this question takes us back to the first moments of the universe, those chaotic, energetic fractions of a second following the Big Bang. During these instants, fundamental forces and particles danced through a hot, dense soup of creation. It was here, in the thick of this primordial chaos, that a mysterious condition took place. A violation of CP symmetry, where in the 1960s, the Soviet physicist Andrei Sakharov proposed that such a violation might hold the answer. He posited three necessary conditions for the observed matter excess. First, there needed to be baryon number violation, allowing protons and neutrons to change into their antiparticles and vice versa. Second, the universe had to violate CP symmetry, meaning matter and antimatter need not act as perfect mirror images. And third, this had to occur out of equilibrium, in the chaotic imbalance characteristic of the early universe. Years later, in 1964, physicists James Cronin and Val Fitch made a groundbreaking discovery that indeed, on rare occasions, certain particles, known as kaons, decay in ways that violate CP symmetry. This violation was subtle but profound proof that nature does have a slight preference for matter over antimatter. Yet there's a catch. The level of CP violation observed was minute, far too feeble to account for the vast seas of matter and structure we see in the universe today. So, the hunt for answers continues, leading scientists to probe deeper into the universe's subatomic heart. In recent decades, physicists have turned to the mysterious neutrinos. These ghostly particles may conceal the key to this cosmic. Some theories propose that if neutrinos are their own antiparticles, as suggested by the Majorana hypothesis, they might have decayed in the early universe in a way that tilted the scales in favor of matter. The pursuit of understanding continues in laboratories and observatories around the world, with experiments designed to catch the fleeting interactions of neutrinos and other subtle violations of CP symmetry. Meanwhile, some bold theories venture further into the mind-stretching realms of the multiverse, speculating that our universe might simply be an anomaly, a rare bubble of matter in a much larger multiverse where most domains fizz out into radiation. The puzzle of matter-antimatter asymmetry remains unsolved, a tantalizing enigma at the intersection of particle physics and cosmology. Each discovery nudges us a step closer to comprehending why there is something, planets, stars, galaxies, instead of nothing. Why the universe didn't self-erase in its earliest instance. It's a profound question, one that leads us to ponder not just the mechanics of the cosmos, but the very reason we exist to ask the question, peering skyward, forever curious. In the realm of the very small, where the classical rules of reality begin to blur and dissolve, particles engage in bizarre acts of seeming magic. One of the most fascinating of these is quantum tunneling, a phenomenon that defies our everyday understanding of how objects should behave, offering a glimpse into the extraordinary world of quantum mechanics. Imagine standing before a mountain. In the macroscopic world, you could choose to climb over it, go around it, or dig your way through it, but you would never expect to simply walk through it. Yet in the quantum universe, particles can and often do just that. To understand this bewildering concept, we need to turn our gaze to the quantum mechanical wave function, a mathematical expression describing the state of a quantum system. Unlike a marble, which occupies a single point in space, a particle in the quantum world exists as a probability cloud. It's not here or there, but everywhere, in all the possible states it could be, until measured. When a particle encounters a barrier, something remarkable happens. Imagine a stream of water flowing towards a dam. Some water will accumulate against it, while in the quantum world, a part of this wave of possibility extends right through the barrier, maintaining a faint ripple on the other side. This is quantum tunneling, where there's a non-zero probability that a particle will appear on the opposite side of a barrier it seemingly shouldn't penetrate. Take, for example, the sun shining in our sky. At the heart of stars, hydrogen atoms are fusing into helium, releasing immense energy. Ordinarily, the repulsive force between their positively charged nuclei would prevent them from getting close enough to fuse. Classical physics predicts that such fusion should be virtually impossible, but quantum tunneling allows particles to sneak through the energy barrier, fueling the stars and providing the light and warmth essential for life as we know it. Quantum tunneling isn't restricted to the cosmic. It's foundational to technology critical to our modern lives. Consider the marvel of tunnel diodes or the operation of flash memory. Electron tunneling through barriers is the basic operating principle of these technologies, fundamental to the function of computers, smartphones, and more. But quantum tunneling is not without its limits. The probability of tunneling depends on the height and thickness of the barrier and the energy of the particle. As these barriers grow thicker or taller, the likelihood of tunneling decreases exponentially. So, while particles composed of fewer entities, like electrons, can, by probability, surmount these barriers, this doesn't scale upwards easily. For larger objects, like biological cells or even whole humans, the probability of tunneling is unimaginably low, bordering the impossible. Despite its regular occurrence in the subatomic world, quantum tunneling remains a mystery even to scientists who study it. Does the particle instantly appear on the other side, or does it somehow pass through the barrier? Recent experiments with ultra-fast. Moreover, some physicists ponder whether tunneling might hint at deeper secrets of the universe. Could these strange occurrences be signals of hidden dimensions beyond our perception, or even testaments to the quantum entanglement that binds the universe together? Quantum tunneling defies the boundaries of the classical world, reminding us of the strange beauty that lies at the heart of reality. It's a testament to how much we have yet to uncover, a challenge to our desire for certainty. In every star that burns, every device that computes, quantum tunneling is at work, unseen, but undeniably influential. So next time you glance at the sun or save data on your phone, remember, somewhere in the vast fabric of reality, particles are defying logic, suggesting a universe richer, more complex, and more mysterious than we have yet to fully realize. This unpreventable dance across barriers tells us that there is still much to explore, from the subatomic realm to the farthest reaches of the cosmos, hinting that our journey of discovery is truly infinite. Imagine standing under a sky full of stars, feeling the vastness of the universe stretching endlessly around you. It's a profound moment, a reminder of the three-dimensional space we live in. But what if everything you experience as three-dimensional, from the stars and galaxies to the very air you breathe, is actually a projection from a two-dimensional boundary far out at the cosmic edges? This mind-bending concept is known as the holographic principle, one of the most intriguing theories in modern theoretical physics. To embark on this journey, we begin at the end of another, a black hole. These cosmic giants, with their immense gravitational pull, swallow everything that comes too close, creating a boundary known as the event horizon, beyond which escape is impossible. In the 1970s, Stephen Hawking discovered that black holes are not entirely black. They emit radiation, now known as Hawking radiation, and gradually lose mass. Over time, they can evaporate completely, leading to a perplexing paradox, the information paradox. In physical theory, information, the detailed history of everything inside the horizons, shouldn't disappear from the universe. But Hawking's evaporation implies it does, contradicting the fundamental premise of information conservation. Enter physicist Gerard Hooft and later Leonard Susskind, who proposed something extraordinary to resolve this paradox. They suggested that perhaps all the information about the 3D reality inside the black hole is actually stored on its 2D event horizon, like an image on a film reel projecting a 3D movie. This idea, breathtaking in its simplicity, became the basis of the holographic principle. It didn't stop at black holes. Susskind and others posited that this principle could apply to the universe itself. In this perspective, our entire universe with all its dimensions could be described by information encoded on a distant two-dimensional surface. In other words, reality as you perceive it, filled with depth, texture, and endless vastness, might be a grand cosmic hologram. Here's where things get even more fascinating. In 1997, physicist Juan Maldacena provided a concrete realization of this principle through what's known as the AD/CFT. He showed that a type of universe modeled with gravity in 3 dimensions could be mathematically equivalent to a universe described by quantum field theory without gravity in 2 dimensions. This showed that gravity and quantum mechanics, 2 theories that often clash, might be reconciled under a holographic framework. This framework suggests something astonishing. The universe's behavior on the quantum level, with all its complexities, might be a reflection of a more straightforward existence on a grand cosmic boundary. All the forces, particles, and their interactions in 3-dimensional space are mere projections or manifestations of processes occurring on this boundary. Yet, this does not imply our experiences are illusions like cinema tricks. Instead, it hints at the extraordinary nature of reality itself, where true substance might arise from a fundamentally different layer of existence. As groundbreaking as the holographic principle may be, it remains a theoretical construct, elegant in its math, yet awaiting experimental proof. Researchers are seeking the pixels of our universe, slight perturbations or traces within space-time that might indicate this holographic nature. If the holographic principle is valid, it will not only unify gravity and quantum mechanics, but also redefine our understanding of space, time, and information. This principle could potentially lead us to a theory of everything, unraveling new paths to understanding cosmological mysteries. We are on a voyage, a boundless and surreal exploration of the universe's true fabric, a journey driven by our quest to understand one fundamental truth: how does the universe work at its most concealed elemental level? The holographic principle doesn't just challenge our understanding of reality, it invites us into a realm where possibilities are as infinite and unfathomable as the stars overhead. With every question raised and each layer of mystery unveiled, we are reminded of the universe's immense depth and its extraordinary potential to inspire awe and wonder. In the world as we know it, the universe is governed by four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These forces are the architects of reality, controlling everything from the binding of atoms to the mechanics of stars. But what if there was another hidden force, a fifth force of nature, waiting to be discovered? This story starts with gravity, the most familiar yet mysterious of the forces. It's the weakest of them, but it commands the grandest scales, holding moons in orbit and galaxies together. Then there's electromagnetism, the force of light and electricity, dictating how charged particles attract and repel. The strong nuclear force binds the cores of atoms, making stars burn and holding protons and neutrons together. The weak nuclear force governs certain forms of radioactive decay, playing a crucial role in stellar processes and particle interactions. Despite their success, these four forces cannot fully account for every phenomenon we observe, sparking whispers of a possible fifth force, a tantalizing concept that pushes the boundaries of physics beyond its current horizon. The search for the fifth force isn't new. In the late 20th century, attempts to unify the known forces led scientists to ponder the existence of this mysterious fifth force. It could be a force that connects the known with the unknown, perhaps interacting subtly with dark matter or dark energy. Fast forward to the 2010s. Physicists conducted experiments hinting at anomalies that couldn't be easily explained by the existing forces. One significant study hails from the Atomki Institute in Hungary, where a research team led by Attila Krasznahorke observed unusual particle behavior during nuclear transition. They detected the unexpected emission angles of electrons and positrons, an anomaly suggesting a new particle might be involved. They're calling this particle X17, named for its predicted mass of 17 mega-electron volts. If real, X17 wouldn't just represent a new particle, it could be the carrier of a fifth fundamental force. Some propose it relates to a dark photon, a hypothetical force carrier that might interact with dark matter, linking the visible and invisible components of the cosmos. The implications are profound. The existence of such a force would reshape our understanding of physics, providing new insights into the fabric of the universe. It could explain anomalies in galaxy rotation, alignments in cosmic rays, or even dark matter itself, filling in gaps that gravity alone cannot account for. Naturally, the scientific community is cautious. Extraordinary claims demand extraordinary evidence. Before accepting the existence of a fifth force, these findings must undergo rigorous scrutiny and replication. Physicists around the world are designing experiments to confirm or refute these results, hoping to capture the elusive signature of this potential new force. But this isn't just about extending a list of forces. Uncovering a fifth force could open doors to a more profound unification of physics, helping to reconcile the quantum world with the cosmos's broader structure. It may hint at novel interactions or phenomena just waiting to be brought to light, an unseen order or symmetry that lies beneath the chaos we perceive. The search for a fifth force isn't just a scientific endeavor, it invites us to re-examine our understanding of reality itself. Are there dynamics at play beyond our immediate perception? Does space-time weave itself in ways we have yet to comprehend? Each experiment and observation, whether it confirms or refutes the existence of a fifth force, adds a piece to the puzzle of fundamental physics. For now, the fifth force remains a compelling possibility on the horizon, a concept that challenges our intellect and fuels our imagination. As researchers peer into the unknown, they are driven by curiosity, by the quest to unravel the profound mysteries of the universe. The pursuit of the fifth force keeps the spark of discovery alive, a reminder that the cosmos is still full of secrets, and we've only begun to scratch the surface of its infinite complexity. Whether or not this force exists, the search inspires innovation, propelling us forward on a path toward greater understanding and insight into the nature of existence itself. Why does the universe exist? It's an age-old question that bridges the realms of science, philosophy, and perhaps theology. Our story begins roughly 13.8 billion years ago with the Big Bang, an incomprehensibly vast explosion that marked the birth of our universe, expanding from an infinitely dense point into the sprawling cosmos we observe today. At that moment, the fundamental forces and particles materialized, setting the stage for stars, galaxies, and planets to form over billions of years. Yet, beneath this narrative lies an unsolved mystery. What caused the Big Bang in the first place? Could it have been a random fluctuation from a still more fundamental level of reality, a cosmic inevitability rooted in quantum mechanics? Physicists often delve into the quantum world for answers, where particles can spontaneously appear and vanish, suggesting a universe just might arise from. But why this universe, with its particular laws and conditions that allow life to exist? The fine-tuning problem poses that very question. The parameters of our universe are precisely calibrated for complexity and life. One hypothesis is the multiverse, where countless universes exist, each with different laws of physics. Among the extraordinary diversity in the multiverse, one universe, ours, happens to possess the right conditions. Yet some propose that our universe's laws are not a mere cosmic accident, but are the result of mathematical necessity, emerging from deeper principles we have yet to uncover. However, this raises a more profound question: why do the laws themselves exist? Whatever the answer, this inquiry beckons us to ponder our place in the universe. Our very existence suggests that either we are incredibly fortunate to reside in this peculiar universe, or that there is a deeper explanation still to be revealed. As we venture further into the cosmos through science or introspection, we grow ever closer to understanding one of the most fundamental questions of all: why is there something rather than nothing? In the realm of the microscopic, where particles dance with waves and the certainty dissolves into probabilities, lies a captive. This puzzle challenges our deepest understanding of the universe and questions the very nature of reality itself. At the heart of quantum mechanics is the wave function, a mathematical description that represents a particle's potential states, a haze of possibilities. When left unobserved, particles like electrons exist in this superposition state, embodying a blend of all outcomes. The famous double-slit experiment perfectly illustrates this. Particles act like waves, passing through both slits, and creating an interference pattern on a screen. Yet, when we try to observe which path they take, the wave function collapses, and particles behave as discrete entities traveling through one slit or the other. This begs the question, what causes the wave function to collapse into a definite state? Is it the act of measurement itself, or does consciousness play a role? The Copenhagen interpretation suggests that particles lack definite properties until observed, but it doesn't specify what qualifies as an observation. Is it a conscious observer, a measuring device, or something else entirely? To address these issues, several interpretations have emerged. The many worlds interpretation posits that all potential outcomes occur in branching parallel universes, leaving no need for wave function collapse. Decoherence theory, on the other hand, explains that interaction with the environment effectively locks particles into certain outcomes, mimicking wave function collapse without the presence of a conscious observer. Despite these theories, the quantum measurement problem remains an enigma, inviting reflection on the role of consciousness, information, and the very fabric of space-time. Is reality fundamentally probabilistic, or do we simply lack a deeper understanding? With every quantum experiment probing deeper into the nature of particles, we edge closer to deciphering this profound puzzle, a mystery that may redefine how we perceive and interact with the world. As physics continues to unravel the layers of the universe, we are reminded of the profound complexity that exists at the heart of reality, a testament to our quest for understanding in the quantum realm. In the vast cosmos, few phenomena inspire as much awe and intrigue as black holes, celestial giants whose immense gravity warps space and time to imaginable extremes. Yet, at the heart of these cosmic behemoths lies an even deeper enigma, the singularity, a realm so perplexing that it defies our current understanding of physics. It is here, in the shadowy depths of these gravitational titans, that science meets mystery. Black holes form when a massive star exhausts its nuclear fuel, collapsing under the weight of its own gravity. As the star's core contracts, its mass becomes concentrated into an infinitesimally small point known as the singularity. At this point, densities and gravitational forces reach infinite values, and the very fabric of space-time curves to infinity. According to Einstein's general theory of relativity, the singularity marks a breakdown of the known laws of physics, a place where our equations and our understanding simply cease to function. But what exactly happens within this realm of infinite curvature? The singularity represents one of the greatest challenges in modern physics, defying both general relativity and quantum mechanics, the two cornerstones of our scientific framework. While relativity describes the large-scale behavior of the universe, quantum mechanics governs the smallest particles. Reconciling these two fields into a cohesive theory of quantum gravity could hold the key to unlocking the singularity's secrets. Such a breakthrough might not only reshape our understanding of black holes, but also provide profound insights into the origins of the universe itself. One of the most tantalizing questions surrounding singularities is whether they might ever be exposed to the universe without the cloaking veil of an event horizon. Known as naked singularities, these hypothetical objects could fundamentally upend our understanding of cosmology and causality. Normally, an event horizon acts as a boundary, preventing information, including light, from escaping a black hole's grasp. However, in certain extreme scenarios, mathematical models suggest that naked singularities could form, allowing the singularity to be visible. This idea challenges the cosmic censorship hypothesis proposed by Roger Penrose, which suggests that nature inherently forbids the existence of naked singularities to preserve the universe's logical consistency. Whether this hypothesis holds true remains one of the most debated questions in theoretical physics. To probe these mysteries, scientists are developing cutting-edge technologies to study the regions around black holes more closely than ever before. Instruments like the Event Horizon Telescope, EHT, are pushing the boundaries of observational astronomy, capturing groundbreaking images of black hole shadows, the silhouettes cast by their event horizons against surrounding light. These observations offer indirect glimpses into the extreme environments near singularities, potentially revealing the subtle fingerprints of quantum gravity at work. The singularity is more than a theoretical curiosity, it is a symbol of the unknown, a frontier that beckons humanity to venture beyond the limits of our current scientific understanding. Unlocking its secrets could have profound implications not only for astrophysics, but for fundamental questions about the nature of reality, time, and space itself. It is a doorway to new realms of knowledge, where our understanding of the universe might evolve in ways we can scarcely imagine. Every insight gleaned from studying black holes brings us closer to unraveling the singularity. Whether it serves as a bridge to parallel universes, a clue to the origins of time, or simply a deeper understanding of the cosmos, the singularity remains one of the most tantalizing puzzles of modern science. As we continue to gaze into the infinite, black hole singularities challenge us to push the boundaries of what we know, urging us to explore, innovate, and imagine. For now, they remain silent sentinels of the universe's greatest secrets, waiting patiently for us to decipher their cosmic code. The night sky, a vast canvas speckled with galaxies beyond number, offers a glimpse into the grandeur of the cosmos. Yet, could all we observe, this seemingly boundless universe, be but a single chapter in an endless, cosmic narrative? The multiverse hypothesis dares us to imagine a reality where infinite possibilities unfold, where universes upon universes coexist within an inconceivably vast expanse. This bold concept expands our understanding of existence, presenting a cosmos far more diverse and intricate than traditional models ever dared to propose. While rooted in speculative ideas, the multiverse hypothesis arises from rigorous scientific efforts to address some of the universe's most profound mysteries. From cosmology to quantum mechanics, various theories suggest that our universe may be just one of many, each with its own unique properties and laws. The idea gained significant traction in the 1980s with the development of inflation theory. This framework, crafted to resolve key puzzles in cosmology such as the uniformity of the cosmic microwave background radiation and the perplexing flatness of the universe, proposed that an exponential expansion occurred in the universe's earliest moments. During this rapid inflation, irregularities were smoothed out, but isolated regions continued expanding independently. These regions could form a stochastic chain of pocket universes. Each parallel to this, the probabilistic nature of quantum mechanics lends support to the many worlds interpretation. According to this perspective, every quantum event results in a branching of reality, creating an ever-growing tree of universes where every possible outcome unfolds. Imagine a cosmic kaleidoscope where every decision, every particle's behavior spawns a new realm, a dizzying cascade of infinite possibilities. Adding further complexity, superstring theory introduces the idea of a landscape of possible universes, each defined by different configurations of 10 or more dimensions. Within this framework, our universe may be one of countless others, each shaped by its own dimensional structure and physical constants. These ideas stretch the limits of imagination, suggesting a multiverse teeming with diversity on a scale that defies comprehension. The multiverse doesn't merely address theoretical curiosities, it also offers potential solutions to some of cosmology's deepest questions. Why is our universe so finely tuned for life? The multiverse posits that we exist in one of countless universes where conditions happen to be suitable for life, a concept known as the anthropic principle. Yet while the multiverse provides elegant answers, it also raises profound challenges about its testability. How can we confirm or interact with realms beyond our perceptual and technological reach? Despite these challenges, observational science holds tantalizing possibilities. Anomalies in the cosmic microwave background, subtle imprints left by ancient radiation, might suggest collisions or interactions with other universes. High-energy experiments, such as those conducted at the Large Hadron Collider, could reveal particles or dimensions hinting at a multiverse. These glimpses may serve as breadcrumbs, guiding us toward deeper understanding. The implications of the multiverse stretch beyond science, reshaping philosophical and existential discourse. What does it mean to be you if infinite versions of yourself exist across countless realities? How do we define free will or identity in a cosmos where every possibility plays out somewhere? The multiverse challenges us to confront these questions, inviting us to expand our understanding of reality itself. Far from being a mere speculative idea, the multiverse is a testament to human curiosity and our relentless drive to explore the unknown. It is a canvas of potential and possibility, a reflection of our boundless imagination and thirst for knowledge. As scientific evidence mounts and theoretical models evolve, humanity stands on the precipice of profound discovery, gazing into infinite horizons that stretch far beyond the observable universe. Whether the multiverse is a physical reality or an intellectual framework for understanding existence, it invites us to dream boldly, to ponder not only what is, but what could be. It is a cosmic mirror, reflecting our deepest aspirations to unravel the mysteries of the universe, one discovery at a time. In this quest, we find ourselves not merely observers but active participants in the grand narrative of existence, a journey of infinite possibilities. Neutrons, fundamental building blocks of atomic nuclei, play an indispensable role in the structure and stability of matter. Inside the nucleus, they bind with protons to form the foundation of atoms, influencing everything from the elements we know to the forces that govern the cosmos. However, outside the nucleus, free neutrons are inherently unstable, decaying within approximately 15 minutes into protons, electrons, and antineutrinos, a transformation known as beta decay. While this decay process might seem routine, it conceals a perplexing anomaly that has baffled physicists for decades: the neutron lifetime discrepancy. The crux of this mystery lies in two distinct methods physicists use to measure the lifetime of free neutrons: the bottle method and the beam method. Remarkably, these approaches yield results that differ by approximately 9 seconds. Though this variance may appear minuscule to everyday intuition, it is monumental in the realm of high-precision physics, where even a fraction of a second can point to new physical phenomena or reveal flaws in our experimental techniques. The bottle method involves trapping free neutrons in a confined space, typically using magnetic or gravitational fields, and counting how many remain after a set period. In contrast, the beam method focuses on a stream of free neutrons, measuring the particles produced during their decay. Despite relying on the same fundamental physics, these methods diverge in their results, a discrepancy that, if more than experimental error, could signify groundbreaking discoveries. Should this discrepancy hint at new physics, the implications are profound. It might suggest unknown particles or forces influencing neutron decay, perhaps even interactions involving dark matter. Alternatively, it could point to deviations in the behavior of fundamental forces, such as the weak nuclear force under extreme conditions. These possibilities could ripple through our understanding of particle physics, challenging well-established theories and sparking fresh inquiry into the unseen fabric of the universe. The stakes are equally high in cosmology. The lifetime of free neutrons directly impacts our understanding of the universe's earliest moments, particularly during the era of primordial nucleosynthesis. In this epoch, shortly after the Big Bang, the delicate balance of neutron decay and proton capture determined the initial abundances of hydrogen and helium elements that serve as the building blocks for stars, galaxies, and life itself. Any adjustment to neutron lifetime measurements could reshape our models of cosmic evolution, altering our understanding of the universe's age, composition, and development. Efforts to resolve this enigma are ongoing, with researchers refining their methods and developing new technologies to reduce uncertainties. Experiments are conducted in highly controlled environments, from deep underground laboratories shielded from cosmic radiation to space-based observatories designed to detect elusive particles like neutrinos. Innovations in neutron trapping techniques, cryogenic systems, and advanced detectors promise to shed light on the discrepancy, potentially revealing its true nature. Beyond the technical challenges, the neutron lifetime discrepancy embodies the delicate interplay between theory and observation, highlighting the iterative process at the heart of scientific discovery. It fuels debates over experimental methodologies and forces physicists to confront the limits of their understanding. In many ways, this puzzle represents the frontier of physics, a wild west of uncharted possibilities, where each clue could lead to a paradigm shift in how we perceive the universe. When the discrepancy is finally resolved, whether through the confirmation of new physics or the refinement of existing techniques, it will underscore the intricate dance between theory and experiment. It will serve as a testament to the relentless pursuit of knowledge that drives scientific inquiry, deepening our connections to the fundamental laws governing matter and energy. Moreover, it will illuminate the cosmic story of origins, linking the ephemeral decay of a neutron to the grand narrative of the universe itself. In the end, the neutron lifetime discrepancy is more than a problem to solve. It is an opportunity to expand our understanding of the cosmos, to challenge the boundaries of human knowledge, and to explore the profound mysteries that lie at the intersection of particle physics and the stars. It reminds us that even the smallest anomalies can hold the keys to the universe's most profound secrets, inviting us to delve deeper into the nature of existence itself. Picture the universe as it exists now, dynamic, vibrant, and teeming with activity. Galaxies swirl majestically through the cosmic expanse, stars burn with unimaginable intensity, and planets harbor the intricate dance of life. But this grand spectacle is not eternal. Far into the future, even these radiant structures will fade and dissolve into the inexorable stillness of the universe's final act, its heat death. At the heart of this inevitable fate lies entropy, the measure of disorder in a system. According to the second law of thermodynamics, entropy in a closed system must always increase, a principle that governs the cosmic timeline. Today, the universe is ablaze with activity. Stars fuse hydrogen into heavier elements, galaxies collide in dazzling displays, black holes devour matter, and life thrives on energy flows. Yet, entropy ensures that this vibrant era is fleeting, a transient phase in the universe's grand story. Over unimaginably long timescales, entropy will spread energy uniformly, leaving no pockets of concentration to power stars or life. Stars will exhaust their nuclear fuel, collapsing into remnants such as black dwarfs, neutron stars, and black holes. The once luminous galaxies will become dark graveyards of stellar remnants, drifting through an expanding, cold void. Even black holes, those titanic gravitational monsters, are not eternal. Through the quantum process of Hawking radiation, they will slowly evaporate, releasing energy particle by particle until they vanish entirely. As they fade into nothingness, the universe will be left with only a sparse mist of subatomic particles, protons, electrons, photons, spread thinly across the vast expanse. The story does not end there. If protons decay, as some theories predict, even these fundamental particles will vanish, leaving behind a universe of low-energy photons and a faint whisper of neutrinos. This bleak reality, a cosmos devoid of structure, interaction, or change, represents the final equilibrium of maximum entropy. With no energy left to fuel transformation, the universe will become a featureless expanse where the distinction between moments and places ceases to exist. In this terminal state, time itself loses meaning. Time, as we understand it, is linked to change, motion, and events. Without energy to drive processes or alter states, the flow of time fades into irrelevance. The universe becomes an eternal stasis, a boundless void where no future or past can be discerned, only an infinite, unchanging present. The concept of heat death paints a stark picture of the universe as fundamentally transient, its vibrant epochs destined to fade into the silent abyss. From the explosive birth of the Big Bang to the quiet finality of maximum entropy, the universe's story is one of transformation, beauty, and eventual stillness. Yet, in this narrative, there is something profoundly moving about the fleeting brilliance of our current epoch, a rare dance of order and complexity in a cosmos moving toward inevitable silence. As we ponder the heat death, we are reminded of the preciousness of this moment in cosmic history. Our existence, though brief, is marked by immense complexity, vibrant life, and the unyielding pursuit of understanding. Each discovery we make and each mystery we unravel weaves a thread into the grand tapestry of the universe's saga. Though the universe's ultimate destiny may be a quiet void, our time within it is a celebration of possibility, a fleeting burst of brilliance in an unfolding cosmic masterpiece. It is a testament to the resilience of curiosity and the enduring beauty of existence, even in a cosmos destined for stillness.